Hey everyone, so we're going to talk about another way that we can factor polynomials. This is going to be related to what's called perfect squares. So if you didn't know, perfect square is usually referring to a number or a polynomial that can be found by multiplying a whole number by itself. So for example, the first 20 squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, and 400. And it's found by taking all the numbers leading up to 20 and squaring them. So 4 is 2 squared, 16 is 4 squared, 49 is 7 squared, 121 is 11 squared. Good way to check to see if a number is a perfect square is put it into your calculator, do the square root of it, and then see if you get a whole number. If you get a decimal, something like 5.673, that's not a perfect square. You'd have to get a whole number in order for it to count as a perfect square. Now, polynomials can also be perfect squares. In particular, what we're going to be looking at more the single term polynomials or monomials. This usually occurs when not only is the coefficient a perfect square, one of the numbers that we just wrote, but also the exponent has an even, the variable has an even exponent. So for example, 49x to the fourth is a perfect square because the coefficient is a square, a perfect square of 7, and x to the fourth is just x squared squared. So this can actually be rewritten like this, 7x squared squared. And this becomes extremely important. So it's kind of what we, again, relating back to what we did in the first part of this class. 49x to the seventh is not a perfect square because even though this first part is a perfect square, the exponent's odd, which means I can't divide it by 2. So that's what you're going to end up doing is anytime you get a variable with an exponent, just divide it by 2, and there you go. So what I want you to do right here is go through all these terms and see which one are considered perfect squares. Pause the video, work and stuff, and we'll go over in a second. All right, so the ones that are perfect squares, 64 is a perfect square. This is 8 squared. 121, which is 11 squared. Y to the 10th, which is y to the 5th squared. I know 25a squared is 5a. This one is a perfect square. This is x to the fourth. Oh, I should write this as squared. Y all squared. This is not a perfect square because that exponent is odd. 225 is 15b4, so that's 15 squared. And this one is 12m third and ninth squared. Again, just take the square root of these terms, and then for the exponents, what you're going to do is half them, and that's going to end up being your answer. I guess I forgot to mention this. This is 15.78. So that's not a perfect square. And again, 3 is definitely not a perfect square. That's actually a prime number. All right. Now, the way that we're going to do it is that if we have an expression that's represented by a difference of two perfect squares, so we have two perfect squares, typically a polynomial perfect square and a constant square, that such as this, 49 minus x squared, then it's going to follow a pattern that looks like this. A squared minus b squared, which is going to be written as a minus b times a plus b. So this is how we're going to factor perfect squares. So if we have this as an example, 16p squared minus 169, what we'll do is we're going to rewrite this to figure out what is essentially the square root of this. So 16 is a perfect square of 4, and p squared can be written as p. So this entire thing can be written as 4p all squared. And then 169, that's 13 squared. So we can rewrite this as 4p squared minus 13 squared. So 4p will be my a term, 13 will be the b term. So now we just plug it into this, a minus b, a plus b. So we end up getting, this can be factored as 4p minus 13, 4p plus 13. Now you can check this yourself to see if this works. And like I said, it will, because what you'll end up having is when you multiply these terms, 4p times 13 and 4p times negative 13, they're going to end up canceling each other out. So the only ones that actually work are 4p times 4p and negative 13 times 13. So here's another example, and we'll do this together. So there's no coefficients here. It's all about the exponents. Each of these exponents can be divided by 2. So if I do that, 4 divided by 2 is 2. Y divided by 2 is 1. 2 divided by 2 is 1. And 4 divided by 2 is 2. So that means I can rewrite this term to look like this. X squared y all squared minus ab squared all squared. So then I just plug it into that pattern of a squared, a minus b times a plus b. So a squared y minus ab squared, a squared y plus ab squared. And that's it. Remember, one of the good things about this concept of factoring is that we can just expand it out again to see if we end up getting this same answer. So we just do what we did in the first part of this course, and we can use that as a check. All right, so here's some practice questions. Pause the video, work on itself, and we'll go over in a second. Okay, so going through all these terms, again, this can be rewritten as x squared minus 7 squared. So the factorization using this difference of two squares is x minus 7, x plus 7. For number 2, so this could be rewritten as 2x squared minus 3 squared. So the factorization will be written as 2x minus 3, 2x plus 3. So the moment you end up figuring out what the perfect square of these are, you end up getting the answer right off the bat, and it always follows the same pattern. All right, now if we go to this one, at first it may not seem like either of these are perfect squares. 2 is not a perfect square and 50 is not a perfect square. This is where we're going to have to continue combining the things that we've done before in order to simplify this. What I can do is I can actually pull out a 2 from here, and this becomes x squared minus 25. Now I can rewrite this as 2 times x squared minus 5 squared, which then means that my factorization will be 2 x minus 5, x plus 5. You want to make sure that you keep this 2 that you pull out throughout the whole process. But this is using the whole greatest common factor in order to simplify it a bit. All right, go into this. The exponents are both even, so this is a prime fact. This can be square rooted, and 1 is a perfect square, so this ends up getting me x y squared. Remember, divide them both by 2. And I can actually just write this as 1 squared. So the factorization will be x y squared minus 1 times x y squared plus 1. This one, so 16 is a perfect square of 4, and then this can be just 4y minus 25 25 is 5 squared. So the factorization is 4y minus 5 times 4y plus 5. Going to here, 100 is a perfect square of 10. So this can be written as 10 minus x squared. So 10 minus x times 10 plus x. All right. And that's basically it. Now, note that there are some things that you're going to want to look out for because we may not give you expressions that can be um, rewritten as a difference of two squares. So you want to make sure that you have this minus sign in front of all these expressions. You want to make sure that the exponents are all even. You want to make sure that this number, the 9 or the coefficients, are all perfect squares. All right, so here's the next set of questions. Pause video work itself. We'll go over in a second. All right, so for this one, once again, 2 and 18 are not perfect squares. So we're going to have to pull out a 2 and get this written as x squared minus 9. This can be rewritten so that it's 2 x squared minus 3 squared. So the factorization is 2 times x minus 3, x plus 3. Going here, so 144 is a perfect square of 12, and x to the 6th, that could be divided by 2 to get x cubed. And again, 1 can be written as 1 squared, so it's going to be 12 x cubed minus 1, 12 x cubed plus 1. This one, so 81 is a perfect square of 9. So this is 9y all squared. Take the exponents, divide them by 2. This is going to be 1, this is going to be 2. So we get xy squared all squared. And the factorization will be 9y minus xy squared 9y plus xy squared. Now this actually could also be rewritten so that it looks something like this. Y squared, if we took out a y squared in the beginning, we could have written it as 9 minus xy, 9 plus xy. If you want, you can expand this out yourself and see that it ends up being the same thing. Going to here. Now this one's easy enough. This cannot be solved, even though n squared is a perfect square and 64 is a perfect square. This is a positive. So this cannot be expanded or factored using difference of two squares. So I'm going to move on to here. So we have 12p cubed minus 27p. So again, at first it may not seem like we have anything. Well, one thing that I could do is, since I have a p in this term and a p in this term, I can pull it out to get 12p squared minus 27. So as far as the variables are concerned, now I have perfect squares, but 12 and 27 aren't perfect squares. So what I can do is think about what type of number these have in common, what common factor they have. I know they both are divided by 3, so I'm going to also pull out a 3. 12 divided by 3 is 4. So far that's good because that's a perfect square. And 27 divided by 3 is 9. Another perfect square. So this can be rewritten as 3p times 2p squared minus 3 squared. Or 3p 2p minus 3 2p plus 3. go into this one. So 121, that's a perfect square of 11. X 8 divided by 2 is 4. And this is all being squared. And then we have y squared. So my factoring will be 11x to the fourth minus y, 11x to the fourth plus y. And that's it. At first, it might take a while to actually recognize what numbers are perfect squares, but you won't have to do any number that's greater than 20. So a lot of those you can just kind of remember. But again, you have calculators, so you just want to make sure that you square root them, see if you get a whole number, and that's it. But the thing to look out for are things like this, where if you don't have a number that can be rewritten as a perfect square, um, then you might need to do greatest common factor or um, any form of common factor in order to kind of simplify it until you do get a perfect square. So here are the three exit questions. Pause video, answer these. So again, that's about the third way that we could factor. By itself, it's pretty straightforward. The whole idea is that you want to make sure that you're able to identify greatest common factor, factoring the trinomials the way that we did it, as well as this dots aspect. So if you have any questions, please let me know. Join the extra help if you are stuck. Answer the rest of the questions in the worksheet, and I'll see you when I see you. Good luck and have a great day.